So when we do problems involving mass defect and binding energy, we're going to have to use these values that are given here in your textbook in Appendix B, which starts on page A.14 in the back of your textbook. All sorts of interesting information here, but the column we'll be looking on this one here called atomic mass given in atomic mass units. These very, very detailed measurements of the masses of the particles involved. Here it is blown up to see some of the particles that we're using here. Here's the neutron that's over there. We're going to be using the proton as well. Now remember, a hydrogen nucleus is just a single proton, and so whenever we deal with the proton, we're going to be using this value right here as the mass of the proton, and then in various places in the table we'll be using the nuclei, the mass of the nuclei of different isotopes. Let's start here with problem 9. All right, we want to find the amount of energy released if the constituent nucleons are combined into a nucleus of fluorine-19. It's just a fancy way of saying we're finding the binding energy when the protons and neutrons come together to form the nucleus of fluorine-19. So I always like to start off by just writing out the isotope. Let's remind ourselves that we have a name and a number. This number here represents the mass number. Remember, mass number is always going to be a whole number because it's just a counter telling you how many things are in the nucleus. What's in the nucleus? Protons and neutrons. So, it's fluorine, so we look up in the periodic table, we know fluorine is element number 9. That's telling you how many protons? 9, right, that's all it's telling you. If it's an atom, that means how many electrons? 9. Good. And then what about neutrons? Well, if there are 19 things in the nucleus, and 9 of them are protons, the remaining must be neutrons, so it's got to be this. So I looked right out like this, 9 protons, 9 electrons, 10 neutrons. Now just to be clear, if you look on the periodic table, here's fluorine, here's its atomic number, which is 9, and then we have this, 18.998. Let's remind ourselves, what is that? That's the average mass of all the isotopes of fluorine that occur in nature. That's a number we don't use. There's no meaning to that for what we do here. This number here is no good. Don't use it for anything. It's useless, okay? The problem will tell you what the mass number is, or there'll be some other way of figuring out what the mass number is, which will tell you that how many protons and neutrons. So, we're going to be using this equation, delta E equals delta mc squared, to find the binding energy. Now, when we talk about delta M, remember this is the mass defect, the difference between the sum of the particles in the nucleus, as if they weren't in the nucleus, and the actual mass of the nucleus. Alright, so we'll take it like this. We'll say there is 9 times the mass of a proton, plus 10 times the mass of the neutron, this is all the constituent particles, the nucleons, minus the mass of the fluorine nucleus as a whole. That's something we can look up on that table. And this is the delta M, the difference between what they are separately minus what they are together, times c squared. And now it's just a matter of looking it up on the table. So again, right over here, here's the neutron, this long number here. The proton, that's just going to be the hydrogen nucleus, that's going to be this number here. And then for the mass of the fluorine, we just find fluorine. And there's only one isotope given, but remember we're using this number here in the column marked atomic mass. So, hopefully your textbook is open, you're looking at this on page A.14. Let's write it out. So we have 9 times the mass of the proton, 10 times the mass of the neutron, and they're all in atomic mass units. Let's put our units on here because, remember, we got to keep careful track of our units. Minus the mass of the fluorine nucleus, which again is given right here, 18.998403. Here it is, 18.998403. I know you could just write down what I have here on the screen, but it's really good for you to actually look at the table in the appendix of your textbook, find it on your own, so you're not just relying on what I have up here on the screen. Alright, so this is the delta M times c squared, but we're not actually going to do that because we want our answer in units that are going to be useful for us, which are going to be mega electron volts. So we're going to use our conversion factor of 931.5 mega electron volts per c squared per u. This is all the units we need to make everything cancel out, right? Because it's per u. Every one atomic mass unit has this much energy in it, so all the u... Oh, so first of all, the c squareds go away. We never actually multiply by c squared. But this has the c squared in it, that's canceled this c squared, and then all the u's get canceled as well. So this is a great little shortcut that will get our answer in mega electron volts. Now it's just a matter of being very particular and careful as you type all your numbers in your calculator. So pause the video, type them all in, see what you get. How many sig figs should we use? Well, while we have a lot of digits in these numbers that we copy right off the table, we only have 4 digits of precision in our conversion factor. So we have 4 digits of precision in our answer. We should be getting 147.8 mega electron volts. If you didn't get that, just pause the video, try it again. You probably just missed a number somewhere. Make sure you're not rounding anything, even though, you know, we are rounding to 4 sig figs. These numbers are as precise as they can be, so let's use all those digits of precision. Okay, it's working? Fantastic. All right, let's try another one. Let's try number 10 here. Now we're doing binding energy per nucleon for nitrogen 13. But we're going to start off the same way. So start off the same way by writing down the isotope, listing out what everything is, and setting up your equation. Okay, so we know it's nitrogen, so it should have 7 protons because every atom of proton, no matter what, has 7 protons. That defines it as nitrogen. And of course, if it's an atom, it's going to have 7 electrons. Not really useful for us, but it's always good. And then I got 6 neutrons. You might say to yourself, well, how did you get 6 neutrons? Because you look at the periodic table, this has 14.007, which is really close to 14, so shouldn't it be 14? And so shouldn't this be 7? But hopefully you got it by now that this number is not what we want. We really shouldn't be using it at all. This is kind of useless. This is just the average of all the isotopes of nitrogen, and we don't care about all the isotopes. All we care about is nitrogen 13. This number is telling us there are 13 things in the nucleus, and 7 of them must be protons because it's nitrogen, which means that leaves 6 things for neutrons. So there's our breakdown. Now here we're doing binding energy per nucleon. So we write this as binding energy delta E over A, right? Because nucleons, those are things in the nucleus. Mass number, which is capital A, is things in the nucleus. So we can just write it as delta E over A. So it's delta MC squared over A. And now if you haven't already, I want you to write it out in a similar fashion to what we did over here, breaking up the delta M. Alright, so we're just tallying up the things inside. That's 7 times the mass of the proton, 6 times the mass of the neutron. It's going to be minus the mass of the nucleus. Right, this is all the particles added up together outside the nucleus. Here they are together as nucleus. We're going to get a difference in those masses. Here's our mass number. Okay, so we look up for nitrogen. Here's nitrogen. Great. Oh, we have a bunch of different isotopes here, right? Oh, we want nitrogen 13, so we find this one here. Don't worry about these others. We want this one, 13.005739. So go ahead and put all your numbers in. Don't just copy what I have. Do it on your own. All right, mass of a neutron, same as before. Mass of the proton, same as before. Here's the mass of the nucleus that we just found from our table. We're going to multiply everything by our conversion factor, 931.5 megaelectron per c squared per u. I left the bottom blank, though, because I want to see if you know what goes there. Did you figure it out? It's 13, right? Because there are 13 things in the nucleus. Nitrogen 13, mass number 13. This is always going to be a whole number. Now, I know these two are similar, but that they're not the same thing. This is the mass of the actual mass of the nucleus of nitrogen 13. There's just the number of things in the nucleus. Megaelectron volts per nucleon. Binding energy per nucleon. Per thing. Okay. So let's see how all the units cancel, right? The c squared goes away with the c squared. All the u's go away. We know we're doing well. Crunch those numbers. Round it to 4 sig figs. Let's see what we get. Did you get 7.239? I hope you did. And remember, our units here are, like it says, megaelectron volts per nucleon, per thing. This could say 13 nucleons or 13 things, right? Okay, so why am I doing one versus the other? Why do we care whether it's binding energy or binding energy per nucleon? Well, binding energy per nucleon might be a little more useful for us. Let's talk about why that might be. Let's look at a graph. Binding energy per nucleon versus number of nucleons versus mass number. Okay? And there's a graph like this in the book. It looks something like this. First, it jumps up very, very sharply and goes down a little bit, and then sort of goes a little wiggly, and then reaches a peak, and then comes back down. Why is this significant? What's it telling us? Well, binding energy per nucleon is rather important because we go back to our analogy with charging emission at the door, right? I charge $1 at the door, so you've lost a little bit of mass when you come into the class. And remember, that $1 is completely refundable. You will get that $1 back if and only if you participate in class. So it sort of binds you together. That represents the binding energy, right? You want that $1 back, so you're going to participate in class. But maybe after a couple of days of doing this, you say to yourself, yeah, you know what, $1, that's I can lose $1. I don't really have to participate. I'm okay with that. As a teacher, I really want you to participate. So, you know, what can I do? I could charge more money, right? Let's say I charge you $5 at the door. You say, oh, $5, okay, well, maybe I don't want to lose $5. So now you're more bound together. But then after a couple of days of that, you say, oh, $5, you know what? I can spare $5. I'm a little bit tired today. So I up the ante. I charge you $100. Now, I don't know if you have $100. You might want to take a loan out from your parents, right? And your parents are saying, you better get that $100 back, right? So now I've charged more energy per student, and now you are now more bound together. Because you are now going to act as a class because you want that $100 refund, don't you? Otherwise, you're going to really be in trouble with your parents. And that's what this is. Binding energy per nucleon. That is actually a more interesting value to us because it tells us, on average, how much the particles are bound together. They've lost more mass, more energy per object. They now have more of a reason to stay together as a nucleus. Just like I charge you more money, you have more of a reason to act as a class. So binding energy per nucleon is the more interesting quantity, especially because of this graph. The graph happens to peak around mass number around 56, which on your periodic table you can take a look at some of the masses, and you can see 56, that's sort of around here in the iron range. Why is this significant? Well, let's talk about stars. Okay, I know it's been a while, but let's talk about stars. Remember, stars are giant balls of hydrogen gas, hydrogen right over here, right? And all these hydrogen particles are attracting each other gravitationally. You might recognize this. We talked about this back in gravitation. And so they attract each other towards the center of the star, and they get so much attracted to each other, they fuse together. When they fuse together, that's a nuclear reaction producing some of the heavier elements. So hydrogen fused together from helium, and fused together with hydrogen from lithium, and so on and so forth. And remember that outward pressure of the energy from these nuclear reactions balances the inward pull of gravity, and for much of the star's life, it's in this equilibrium state. But in these processes, it's constantly fusing these nuclei together, forming heavier and heavier and heavier elements. Eventually, once it starts forming iron, well, now it's at the peak of binding energy per nucleon. It turns out to form something past iron is not energy efficient anymore, and so the process stops. And so eventually, after many, many billions of years, once a star has used up all of these lighter elements and fused and fused and fused and eventually formed to iron, well, then the process stops, and now there's very much less outward pressure of the energy, and now gravity starts to win. And this is the demise of the star. This is how the star starts to die. Remember, it starts to collapse in on itself. We talk about all different things that could possibly happen with black holes and neutron stars and stuff like that, but one of those is a nova, right? If sometimes the inward pull, the size of the star is enough, the inward pull fuses these elements together, it's enough pressure to do so, and it starts to fuse some of the heavier elements, then explodes outwards, and so these heavier elements, the ones past iron, all these ones over here, except for the man-made ones, they get ejected into the universe in this explosion, the death of the star, this nova or supernova. And now these heavier elements, they go shooting off into the universe, and maybe they cluster together to form another star somewhere else, or maybe a planet somewhere else, or maybe some of the things on the planet, like you and me. You see, every atom in your body was once part of a star. You are truly star children.